Okay, so let's look at number one. We want to solve for y. So Casey, you were starting to tell me what to do, so why don't you walk us through this one?
Subtract 3x.
Okay, minus 3x.
2x equals negative 3.
You mean 2y, right?
2y
Uh-huh.
equals negative 3x plus y.
Good, now what?
Divide by 2.
And what do we end up with?
Y equals 3 over 2. Need negative 3 over 2. X was 3.
No, we have 5 over 2.
Oh,
Just
wait,
5
yeah.
over 2.
That's right, we're dividing that in subtraction.
And you can just leave that as 5 over 2.
And then you're done.
Yeah, then we're done. Okay, Garrett, take number 2.
Minus 1. Right.
We're solving for y.
Plus Jason.
Good. Okay, what do we
Y
want?
equals 2x plus 1. Divide by 4.
Okay.
Y equals 2, or 1/2.
1/2, good, because 2 over 4 reduces to 1/2. X plus 1, because 4 divided by 4 is 1. Okay, good. Casey, number 3.
Minus 6.
Good. And we end up with,
Negative 3y equals 9x minus 6.
okay, now what?
Oh, divided by negative 3.
Good. And we get,
Y equals negative 9/3.
what is negative 1/3? Simplify that now.
3 of 1. Just
Mhm.
3.
Or just 3, negative.
Negative
Negative 3. Okay, so negative 3x.
Minus plus 2.
Plus 2, good, because we've got negative 6 divided by negative 3 is positive 2. Okay, number 4 is a little bit tricky. We actually won't see too many like number 4 in what we're doing now. In order to solve for y, right now y is on the bottom.
Multiply by 1.
Excellent, good. Good, you didn't have to think about that. So we're going to multiply by y to get it out from the bottom. So we multiply this side by y, and that will cancel the y's, and multiply this side by y. So we end up with 3 minus x equals 5y.
So then you just divide by 1.
Good, 5 by 5. And our y's over on the right this time, but that's okay. What do we end up with?
3x minus 5x.
No, not minus 5x.
Negative plus
This
5x.
is like 1.
So,
Only 1 left.
Yeah, minus 1/5 x. Okay, good. Any questions?
You know who Dirk is, by chance?
Okay, so today we're just going to be solving systems of equations by graphing. So we will graph problems to determine the solution for a system of equations, and then we'll also tell whether a system has one, none, or infinitely many solutions. We'll talk about what a system is on the next page. Let me move this, put it down here. Okay, a system of equations consists of 2 equations, each with the same 2 variables. So a system of equations might look something like this. You might have x plus y equals 10, 2x minus y equals 5. Could be anything, but it's 2 equations that have 2 of the same variables. You can actually have systems of equations that have more than 2. You could have a system with x, y, and z. You would need 3 equations in order to solve one. When I was in college, I took a math called matrices, and we would solve systems of equations that had lots of variables. Like you could have 10 variables and 10 equations and still solve it. And there's all kinds of rules for how to. You just kind of set up all the numbers in columns, and then you do things to the columns until you solve it. It's like a big puzzle. It was fun. It was my favorite math ever. Okay, so we can take each equation and we can graph the equation. Whenever we graph the line for a linear equation, that line shows us all the solutions for the equation. So if we look at this first equation up here, x plus y equals 10, this one, we can put lots of different numbers in for x and y, right? Like if x was 5, y would be 5. If x was 2, y would be, no?
What?
2 plus what is 10?
Not freaking 8.
8, there you go, 2 plus 8. So there's like an infinite number of things we could put in, and we could get a bunch of different pairs of solutions. So when we graph a line, that shows us all of the possible coordinates that make each equation true. So when we have a system of equations, we want to know what x and y make both of them true at the same time. And so the solution to a system is just a single point. It's usually a single point, but as we'll see later, sometimes it can be more than one. It's the point where the two equations intersect. So we're going to graph both equations, and then we're going to look at where they intersect, and that's the point that we will call the solution. Any questions? Okay, so when we solve a system by graphing, we have to remember how to graph equations. How would we graph this first equation? Y equals x plus 2. It's in slope-intercept form. Remember that? What did I do first?
Y equals x plus b.
Yeah, it's already in that form. So what is the y-intercept in that equation?
1.
No?
No.
Remember, if we have y equals mx, good, plus b, the b is your y-intercept. So this 2 up there is your y-intercept. So that's where it crosses the y-axis. So we're going to put a point at 2. How do we get our next point? Up 1 and then over 1. Because in front of the x, we actually have a 1. So our slope is 1. Our y-intercept for this was 2. Our slope was 1. So we go up 1, over 1, and we put a point there. Now, when you're solving systems by graphing, it's really important that you use a ruler and that you use graph paper. So I'm going to give you this ruler. Otherwise, your lines will end up a little crooked and your solution won't be at the right point. Okay, so that's my first line. Let's graph the next line. Where would I put my first point? -2. And how about my next point? Good. Slope is 3, so we go up 1, 2, 3, over 1.
21.
Slope was 3, so we go up 3 over 1. Good?
But wait, why did we start -2? Oh,
Because the y-intercept was negative 2.
Gotcha.
Okay.
Do not think that good.
And then over 1.
Yeah, we went up 3 over 1. Okay, so we end up crossing at what point? The lines cross right about here. What would be the coordinates for that point? Good. 2, 4. So x is 2, y is 4 for this point. And then once we get a solution, then we check it to make sure it really is the solution for both equations. So the first equation we had y equals x plus 2. If we put this 4 in for y, and we put the 2 in for x, we get 4 equals 2 plus 2. Does 2 plus 2 equal 4? Then we're good. When we check the second equation, it's y equals 3x minus 2. We put 4 in for y. We put 2 in for x. Is that equation true? So we know that we got the right answer. You never have to wonder with systems of equations because you can always check. Okay, next one is one for you to try. I'm going to pause this for a minute.
That should prove me.
Okay, so let's graph this and see what our solution is. First equation, y equals 2x plus 4. We're going to start at 4. And then we're going to go up 2 over 1. It's helpful when you're trying to get really straight lines to graph at least another point. I'm running out of room on the graph to go up. So instead of going up 2 over 1, I could go down 2, left 1, and make my line this way. It helps the line be a little straighter if you have 3 points to look at, since our points are not perfect and our lines are not perfect. Okay, then my next line is y equals x plus 2, so we start, our y-intercept is 2. Our slope is 1, so we go up 1, over 1, and I'm going to go up 1, over 1 again.
Yeah, so you ended up where I did.
And even my line is off.
Yeah, your line ended up exactly how
Yeah,
mine did, so
but it
it's like
shouldn't
good.
have. It should have been.
But this is when you just make that educated guess.
Yeah, this is where we make a monster point in this case. My high school algebra teacher always made monster points.
That's what I did.
Our lines should have crossed down here, so we'll just make this
I just
nice
do
and big.
this, you-
What would be the coordinates for that point?
2 and 0.
Negative 2 and 0. So our coordinates would be negative 2 and 0. You can see my line kind of goes on this side of the point a little bit. If it had gone.
So it'd be y equals negative 2x. minus
Well, we can
0.
check, so y equals 2x plus 4, and y is 0, 2 times negative 2 plus 4, does that equal 0?
No. Yes.
Yes, it does. And the next one, we could just check in our head, if we put negative 2 in for x up here, we have negative 2, negative 2 plus 2, which is 0. That one's pretty easy to do. Okay. I want to show you what happens if you sometimes end up with infinitely many or parallel, no solutions, which would be parallel lines. So let's take a look at this one first. What's the problem with graphing this system of equations? No, the half is okay. Just look at both equations. Can you graph both equations easily?
No. It was solve the first one.
Yeah, we have to solve the first one. We could use standard form to graph it, but let's stick with slope-intercept for now. So let's convert this first equation to slope-intercept form. So we'll do that down here. So we have 2y minus x equals 2. This is where our warm-up came in. We're going to solve for y. What would I do first? Add x, so we end up with 2y equals 2 plus x. Now what do we do? And what do we end up with? Y equals, no, 1 over 2, 1 half. X. Okay, so we have this equation, and we have the second equation up here. We're working with this one and this one. What do you notice about those two equations? Garrett, what do you notice about those two equations? Yeah, they're the same equation. Our 1 and our 1/2 x are on two different sides, but they're the same equation. So when we graph them, the y-intercept is 1 for both of them, and we're going to go up 1, over 2. We'll do that again, up 1, over 2. So we get the same line. If we were to graph the next one, we'd have two lines superimposed on top of each other. So remember, the solution is where they intersect. So where do these two lines intersect?
All the way.
They intersect everywhere, right? Because they're the same line. So what does that mean about how many solutions they are?
Infinite.
Right. They intersect at all points. So you have an infinite, I'll say infinitely many solutions. Now let's take a look at another example. Okay, these two equations are both solved for y already, so we can just graph them. Casey, where am I going to start for the first one? The graph. 2, and what do I do now?
Go over 2. There now. 10. You go up 1 over 2.
Not up 1 over 2.
Up 2 over
Up 2 over 1, good.
Mhm.
Up 2 over 1. I'm going to do it again. See if we can do better getting these lines to look straight. tell me how to graph the second line. Good. Okay, up to over 1, up to over 1 again.
See no solution with that.
Yep. Why would it be no solution?
Because they never meet.
They never intersect. They're parallel lines. Never intersect. So there is no solution. Do the equations themselves, if we look over here, does this give you any clue that they're going to be parallel? Is there anything like that? What?
Because instead of the -1, you got the +2.
Okay, so the y-intercepts are different. The slope is the same. Good. So if they have the same slope, they're going to be parallel. So if you see the same slope but different y-intercepts, you know there's no solution.
Just say
Right.
like, no solution.
Yeah.
Like the next one, no solution.
Okay, so this one, Casey just pointed out, we don't even need to graph it because we can see they have the same slope, they both have a -1, but they have different y-intercepts. So when we graph them, we'll just do a quick rough graph. We have -3 and a slope of -1, so we go down 1, over 1. I'm just gonna do a really rough hand-drawn, I'm not gonna use the ruler because we know what we're gonna get. And then we also have a line that starts at 5, goes down 1 over 1. So we're going to have 2 parallel lines, no solution. Okay, let's take a look at the next one. Can we tell anything about this one just from looking at it? Infinite y. Okay, so let's solve for y. What do we have to do to solve for y? Just divide by 3, good. So we end up with y equals 3x minus 3, which is the same as our first equation. So we have the same line, so we have infinitely many solutions. If we graph this, we'd start at -3. We'd go up 3 over 1. And again, I'm going to just do a hand-drawn graph here since I already know what's going to happen. And the other line will be right on top, so I'm going to see one line in our graph. Questions? Okay. Let's go on and sum this all up. So if there's one solution, the lines intersect at how many points? 1 point. And are the slopes the same or are they different? If it has infinitely many solutions, the lines intersect at how many points? All points. Are the slopes the same or different?
Identical.
They are identical or the same because they are the same line. Okay, if there's no solutions, the lines intersect at how many points? None, or at no points. What about the slopes? Are the slopes the same or different? They're the same. And the lines are, no, they're not identical.
Not identical, different.
And they're going side by side.
Parallel.
Parallel. Okay, your assignment, there's 2 parts to your assignment. The first is a worksheet. The reason I'm giving you a worksheet instead of the textbook is because some of the textbook answers are really far out. Like you'll get an answer that's like 824, which means your graph has to be really huge and super accurate for you to get the right answer. So I have a worksheet that has the graphs already on it, so you don't have to draw them, and it makes it a little easier to see. So the first part of the assignment is to do the worksheet. The second part is, in order to practice the infinitely many, you need to use your textbook. And I did all of these and they all work out nice and neat, so there's nothing unusual there. It's page page 368, 22 through 30 even, so there's only 5 problems. If you want, you could start with your textbook, get that done while you're at school, and then take the worksheet home.
22,